This lesson is on Boyle's law. Now, before we jump into Boyle's law, we're going to do a little bit of mathematics. So I have taken my paper, I just folded it in half, and on the left side, I'm going to look at y divided by x equals 2. And on the right side, I'm going to look at x times y equals 12. So on your paper, we're going to make a little data table and then do a graph for each of these equations. All right, and we're only going to look at positive values of x and y, so we only need our first coordinate. All right, so x and y. And we can also write this, of course, just bring the x over as y equals 2x. They're equivalent. But there is a reason I have it written like that. All right, so let's just put in some easy values of x. So if x is 1, y is 2, if x is 2, y is 4, x is 3, y is 6, x is 4, y is 8. Let me do one more. X is 5, 2 times 5 is 10. So we're just going to make a graph now. So here's our x-axis and our y-axis. Oops, I shouldn't have written them so close. Oh well. All right, so x, 1, 2, 3, 4, 5, and then make y. We'll go up by 2s. 2, 4, 6, 8, 10. Okay, and then we'll plot our points. So when x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 6. When x is 4, y is 8. When x is 5, y is 10. And we can see that we have a straight line because this equation, y equals 2x, that is the equation of a line. Our b, or y-intercept, would be 0. But we can't have x equals 0 when it's written like this because we can't divide by 0. Okay, so straight line. So let's just connect those points on our graph. Okay, let's do the same thing for our equation x times y equals 12. So we'll make our data table. And again, we're just going to put in easy values of x to get y. So if x is 1, then y has to be 12. If x is 2, 2 times 6 equals 12. If x is 3, 3 times 4 equals 12. 4, 3, 6, 2, 12, 1. All right, and let's make a graph for that. So I'm going to go up by 2s for my x-axis. 2, 4, 6, 8, 10, 12, and same thing over here. 2, 4, 6, 8, 10, 12. All right, and now we will plot our points. So when x is 1, y is 12. When x is 2, y is 6. When x is 3, y is 4. When x is 4, y is 3. When x is 6, y is 2. When x is 12, y is 1. So we can see we do not have a straight line. So we're going to do what is called a best fit curve. We don't want to connect the dots because we can see that the data makes our graph a curve. So let's do our best to get a best fit curve through our points. Okay, so our graphs look very different. Here, our x and y are our variables, and this number 2 is a constant. And we can see that when x is small, y is small. As x increases, y increases. For this graph, we say that y varies directly with X. That means if X increases, Y increases. The bigger X gets, the bigger Y gets. Over here, now our X and Y are the variables. 12 is a constant, it stays the same. So here, when X is small, Y is really big. And as X gets larger, Y gets smaller. So here, X is really large, Y is really small. So we say that Y varies inversely with X. So here as X goes up, Y goes down. Over here, where Y varies directly with X, all of our conversion factors are in this form. So this is all conversion factors. Are in the form of Y varying directly with X. Here, an example of where we have this, let's take an example of a lottery. And the ticket hits and the prize is $1,000. Well, if one person bought the ticket, the one person would get $1,000. If two people chipped in to buy the ticket, they would each get $500. If 10 people all chipped in, then each person would get $100. If 1,000 people chipped in to buy one ticket, they would each get $1. So as the number of people who contributed to the ticket increases, the amount of money each person gets decreases. So that is an inverse relationship. So whenever we have our variables, y over x equal a constant, so constant doesn't change, y over x are our variables that change. This is a direct relationship. And whenever we have two variables that multiply to give a constant, then we have an inverse relationship. Okay, so we're going to be using that as we look at the different gas laws that are coming up. And our first law is Boyle's law. And this was in 1662. So to get a little perspective on that date, Dalton's atomic theory, that was in 1808. So this is hundreds of years before that, way before that. So this was before the idea of the atom was accepted. At this point in time, Isaac Newton, he was about 20 years old. So a lot of science was being explored then. This was right after the time of Galileo. Okay, so Boyle's law says, for a fixed amount of gas at constant temperature, the pressure varies inversely with the volume. Pressure varies inversely. So that means that P times V equal some constant. And we use K to represent a constant often in chemistry. P times V gives us our constant. So if we look at a graph of that, what would that look like? Well, we've already done that. So if we have P and V, we know if they vary inversely when when volume is low, pressure is high. And as the volume increases, the pressure decreases. We're going to get a slope like that. Now let's look at this law in terms of our four factors that we talked about for the ideal gas law. And this law includes all four of those factors. It says for a fixed amount of gas, so amount of gas, that is our moles, that is our N. We're at constant temperature, there's the T, the pressure P, varies inversely with the volume V. So even though they didn't have the idea of atoms, they still could keep the amount of gas the same. Fixed amount says the amount of moles or the grams is not going to change. Okay, so let's try to visualize what is going on here. So we're going to look at a container with a piston. And we'll put some gas in our container, and we want to keep the amount the same, so we're gonna we'll put in 10 gas particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's our gas. And remember that our gas particles are constantly bumping around into each other and to the sides of the container. And it's the force against the sides of the container that causes our pressure. Now, so we have some pressure, we're just going to call that P1, and we have some volume, we'll call that V1, and that has to equal some constant K. And that K will depend on the amount of moles and the temperature. All right, so what we're going to do is we're going to push that piston down. There's our container. We're going to push the piston down. So now we're squeezing our 10 particles into a smaller volume. 1, 2, 3, 4. There they are. So now we have a new pressure. We're just going to call that P2. And we have a new volume, V2. And that has to equal K. As long as the number of moles stay the same, which they are, we have the same number of particles, and the temperature stays the same, this K is a constant, has to equal this K, that is a constant. And let's just kind of get an idea of what's going on here. If the temperature stays the same, the speed of the particles stays the same. So what happens to the pressure when our particles don't have to travel as fast? Here the particles have to travel further to hit the sides. Here they have to travel not as far, so they hit the sides of the container more often. So if the container sides are getting hit more often, it means the pressure increases. The pressure increases because the particles have to travel less far to hit the sides of the container. So as the volume goes down, the pressure goes up. That is what Boyle's law is saying. Well, if P1, V1 equals some constant K, and P2, V2 equal that same constant K, that means that P1, V1 has to equal P2, V2. We can just substitute in with algebra. So this is the form of Boyle's law that we use most frequently. And we could raise the piston up a little bit and have a P3, V3, but no matter how far up and down we move that piston, this value holds, unless we push it down so far that our gas would turn into a liquid. Okay, so let's see how we're going to do a problem with this. Okay, here's our problem. A gas in a container with a piston has a volume of 750 decimal point milliliters and is at 765 torr. The piston is pushed down until the volume is 420 milliliters. What is the new pressure? Temperature is constant. So we have changing conditions here. So we're going to go back and put the values, or not the values, the quantities in here. So a gas in container with a piston has a volume of 750 milliliters. That is our starting volume, so we're going to call that V1. And is at 765 torr, so this is our pressure P1. The piston is pushed down. Now we have a change until the volume is 420 milliliters. So this is our new volume that we're going to call V2. And we're asked for the new pressure, which is P2. So now we're going to write our equation for Boyle's law. P1, V1 equals P2, V2. And now we're going to substitute in. Now, when we use the ideal gas law, because we had that ideal gas constant R that had specific units, we had to use the units of R. We don't have R here, so we do not have to use the units of R. But what we do have to have is the same unit. So if pressure is in millimeters of mercury, then it has to be in millimeters of mercury here. If volume is milliliters, volume has to be milliliters. So it doesn't matter what our units are, they just have to be the same on both sides of the equation. All right, so let's substitute in. So P1, so I don't have to change that to atmospheres. I can just leave this as 765 torr. Times V1, I can leave that in milliliters. 750 milliliters. Equals P2 is what I'm looking for, and V2 is 420 milliliters. So milliliters is on both sides of the equation. If I divide by milliliters, the milliliters cancels out. I have to get P2 by itself. Divide this side by 420. Divide this side by 420. That cancels out. I have P2 by itself. And now let's do the math. Okay, so we have 765 times 750 divided by 420 equals. Okay, so let's see. I'll write the number down and then we'll do our sig figs. So my calculator tells me 1366.07, and I need 3 sig figs. 1, 2, 3. I have to maintain the magnitude of the number. So 1370 torr is my answer. All right, so to distinguish this between an ideal gas law problem, in the ideal gas law, the problems, we only have one set of conditions. We just have some gas in a container and there's no change to the container. Here in Boyle's law, now we have a change to the container, which results in a change of the volume and the pressure. All right, that's it.